Hello, everybody. This is Professor Ken. Hi. I'm going to show you how we can find probabilities of given X scores. We learned already how to do that with Z scores, and how we can be given probabilities and find the X score that corresponds to that. So first of all, I'm going to share my screen with you. And I'm also going to stop my video because you don't need to be seeing me. I can turn it on later if you need me to. Okay. So I have a PowerPoint presentation for you, and um, a lot of it has to do with pulse rates. So that's why we have this picture here. Okay, so for a quick review, what did we do last class? We learned that a normal distribution, that's the bell curve, can be mapped to z-scores. And we learned to find a probability of an event being greater than or less than a z-score. We use the z-table with that. We learned how to find a z-score if we know the probability. And we learned how to draw a normal distribution graph with the z-axis. We learned that the probability of a z-score occurring is 0 because you can never have exact if it's continuous distribution. And what we're going to do now is, so here's our normal distribution graph with our z-axis. And how could we find a z-score for a given percentage? All right, well, there's a given percentage. Let's suppose that percentage is 0.1587. How do we find the z-score? Well, we look on our z-table. But the z-table wouldn't tell us 0.1587, it would tell us 0.8413 because it shades to the left. So we want to find a z-score so that the probability of getting greater than z is 0.1587, which is the same thing as the probability of less than z being 0.8413. So we find 8413 in the table, and the corresponding z-score is 1.00 right there. Okay, so the z-score for less than or equal, for a probability of the z being less than or equal to 84.13% is 1.00 is the z-score. Okay, let's try another one. Find the probability that z is greater than negative 1.75. Okay, here's our normal distribution graph with our z-axis. And there is negative 1.75. It looks like a little e, but it's really a decimal point. All right. So when I put my partition up at negative 1.75, I look at my negative z-scores, and I find that the area to the left is 0.0401. So what's the probability of being greater than negative 1.75? That's everything over here, this whole area under the curve. So that would be 0.9599 because 0.9599 plus 0.0401 is equal to 1 whole. So the probability that z is less than negative 1.75 is 4.01% or 0.0401. Therefore, the probability that z is greater than negative 1.75 is 1 minus that, or 95.99%. Let's try another one. Find the probability that a z-score will fall between negative 0.89 and 112. So here's our normal distribution graph with our z-axis. All right, so we put a partition up at negative 0.89 and another partition up at 1.12, and we shade in between. Now we're trying to find the area under that curve. So the yellow area is what we're trying to find, and whatever that area is, that will be our percentage. So we need to find the area under the curve. All right. So the probability of less than negative 0.89, that's all this area here, is 0.1867. And the probability to the left of 1.12 is 0.8686. So from this partition all the way to the left, all this is 0.8686. So if we subtract the 0.8686 area, if we do the 0.8686 minus 0.1867, that'll give us this yellow area. So the probability of negative 0.89 being less than z, which is less than 1.12, would be equal to the probability that z is less than negative 1.89 minus the probability that z is less than 1.12. Actually, it's the other way around. So it's equal to 0.8686 minus 0.1867 is equal to 0.6819 or 68.19%. So if this whole area is 100%, then this yellow area is 68.19%. So it's somewhat more than half. And it looks that way. So our answer is reasonable. All right, so this was all review from last week. And now we're ready to embark upon some new material. So z-scores aren't real data. They are scores that were converted from real data into normalized data. But today, we're going to use the real data. Those are called x-scores. So now we see that we have our normal distribution graph with a z-axis, which is the normalized data. We also have an x-axis, which is the real data. So pulse rates for females are normally distributed. The mean is 74 beats per minute, and the standard deviation is 12.5. Don't worry about that 61.5 yet. So on the z-score, the mean is 0, but down here, it would be 74. So first construct the graph. The z number line represents the standardized scores or z-scores, and there they are. So this is 1, 2, 3. It also represents 1 standard deviation away from the mean, 2 standard deviations away from the mean, but those are also the scores. Now we can make an x number line that represents our real data or x scores. That's this number line here. So we see that our mean is 74, so that goes underneath the 0. Now, 1 standard deviation away, we would add 12.5. 2 standard deviations away, we would add 12.5 twice. 3 standard deviations away, 12.5 3 times, and subtracting it going this way. So that's why we have these points on the x number line, because for every standard deviation we go to the right, we add 12.5. For every standard deviation we move to the left, we subtract 12.5. So here's our data again. Now we can solve a problem. Now that we have a z-axis and an x-axis, we can find the probability of real data occurring. So what percent of the population has a pulse rate between 49 and 86.5? All right, here's 49 and the z-score is -2. Here's 86.5 and the z-score is 1. So we want this area here between -2 and +1. Ah, there's the shading. So we want this area under the curve. We see that it does look like it's more than 50%. So to the left of 1, the probability is 0.8413. To the left of -2, it's 0.0288. So our answer for the shaded area is going to be 0.8413 minus 0.0228. And we get 0.8185. So the probability of falling in the shaded area is 81.85%. So that means that the percentage of the population that has a pulse rate between 49 and 86.5 is 81.85% of the population. So more than 3/4, actually, more than 80%. Okay, so that's the first one. Now, I didn't show you how to convert z-scores to x-scores or x-scores to z-scores, but I will now. So we're going to use the same data set where the mean was 74 for pulses. And here's our normal distribution curve with our z-axis and our x-axis. So we need to be able to change x-scores to z-scores. A z-score is the difference between the x-score and the mean divided by the standard deviation. There's the formula. So if we know the x-score and we know the mean and we know the standard deviation, the z-score will equal the x-score minus the mean divided by the standard deviation. So we know that in this case, the mean is 74. So 74 minus 74 divided by 12.5 is 0. So that's why the z-score is 0. So what is the z-score for 100 beats per minute? Well, x is 100. The mean is 74. The standard deviation is 12.5. Plugging and chugging, what do we get? 2.08. So if this is 74, 100's right around here, and the z-score is 2.08. There we have it. Now, if we wanted to find the probability of having a pulse rate less than 100, you would look up 2.08 on the positive z-score chart. Whoops. And that would be all this area, and that change that to a percent, and that would be the percentage of the population whose pulse is less than 100. We'll do something like that now. So finding a probability with x scores, like greater than x or less than x, if you know the mean and standard deviation, there's a step-by-step procedure. Number one, identify the mean and standard deviation. Number two, draw the normal distribution graph with the x and z axes. Plot the mean and the x score in the probability question. So in the question that we were given, shade the desired area for which the area is the answer to the probability question. Convert your x score to a z score. Use the z-score table in the back of the book to find the areas of the graph, and then answer the question. So although there is a step-by-step procedure, we still have to think and adjust based on where the area is. Let me show you what I mean. So make sure the answer is reasonable. So if the mean of the pulse is 74 and the standard deviation is 12.5, so that hasn't changed, find the probability that a pulse rate is greater than 79. Now, if the mean is 74, that means 50% of pulse rates are greater than 74. So greater than 79 should be less than 50%. So step one, the mean is 74 and the standard deviation is 12.5. All right, now I hand drew it because this is what you're going to do on the homework. So there's our z-axis and our x-axis. And we see that the mean on the z-axis is 0 and the mean on the x-axis is 74. But we're trying to find greater than 79. So that's the area we're trying to find out right in here. Now, if we look at, convert this to a z-score, we get 79 minus 74 divided by 12.5, plug and chug, and we get 0.4. So our z-score right there is 0.400. Now, if we look it up on the table, we're going to get a value bigger than 50% because it's going to tell us shading to the left. That's all of this. So I'm continuing over. No, I'm not. We didn't finish, so I can't believe I didn't finish this. So you'd get the percentage here and subtract it from 1, and that would give us the z-score. That would give us the probability that a pulse rate is greater than 79. All right, let's take a look at this one. Sometimes we get a z-score from the graph, and then we must change out the z-score to an x-score. What's the pulse 75th percentile? That's the question. So since z is equal to x minus mean divided by standard deviation, if we want to get x by itself, we multiply both sides by standard deviation, and we add the mean, and we get x equals the z-score times the standard deviation plus the mean. So we would want to, for 75th percentile, we want to shade the area in question, which is all of this. I don't know why. There we go. And we know that that area is equal to 0.7500. Then we want to use the table and work backwards to find the z-score. So when we look at the table, we see that the z-score is 0.67. Now we need to convert that z-score to an x-score. So we calculate the x-score that corresponds, and there it is, and we get 82.37. So right here is 74. Over here is 82.37. So that means 82.37 beats is the 75th percentile. There we have that. And here's our answer. The pulse for the 75th percentile is 82.37 beats. Okay, let's try another one. A pulse in the bottom 5% or top 5% is significant. That means it's worrisome. Find the significantly low and the significantly high pulses. In other words, find a pulse that X is less than 0.05 or the pulse that X is more than 0.05. The probability is less than 0.05 or the probability is more than 0.05. So we start off with, as usual, our normal distribution graph with a z-axis and an x-axis. Now we know our mean is 74, standard deviation is 12.5. There's our shaded region. So we want to find the z-score that's going to give 0.05 here. And then we would want to find a z-score over here that's going to give, to the left, 0.95. So our z-scores that do that would be negative 1.64 and positive 1.64, although I think I forgot to put it there. So when we change negative 1.64 to an x-score, we get 53.5. So this would be 74 right here. Over here is 53.5. And over here is going to be 94.5 by plugging and chugging. So our x-scores are negative 1.64 and positive 1.64. And those are our z-scores. Our z-scores are negative 1.64 and positive 1.64. When we run it through the formula to get our x-scores, we get 53.5 and 94.5. What formula was it? This one right here. So the z-score times the standard deviation plus the mean. And that's what we have right here. So the z-score times the standard deviation plus the mean to get 53.5 over here, and our z-score times the standard deviation plus the mean, that should be 74, to get the x-score over here. And there's our x-scores. So from the previous slide, the pulse rates that are less than 53.5 and greater than 94.5 are significantly low and significantly high. That's how we answer that question. Okay, I should have said this at the beginning of the video, but after each slide, it's generally a good idea to pause the video and take some notes. So I hope you've been doing that. Let's try another one. All right, low birth weight are those less than 5.5, which, we use in medical, we use the metric system. So 2,495 grams. If you're less than 2,495 grams, you're considered low birth weight. Birth weights are normally distributed, which means they're on the normal distribution graph. And the mean is 3152, and the standard deviation is 693.4. So what percentage of births are low birth weight? Well, there's 0 on the z-axis. We know our mean is 3152, and our standard deviation is 693.4. So there's our mean. The mean on the x-axis corresponds with 0 on the z-axis. All right. Below 2495 is low birth weight, so it's this area that we're trying to find out. Now, we can see that this x-score is going to convert to a negative z-score. Then when we find the percentage or the probability of that negative z-score, that will give this area here. So how do we find our z-score? There we go. Z is equal to the x-score minus the mean divided by the standard deviation. We get negative 0.94. So that's the z-score right here. Negative 0.94. When we look it up on the table, we see the area is 0.1736. So what does that mean? 17.36% of births are low birth weight. All right. Why don't I give you guys one more to do? I'm going to go home and add a new slide. I'll show you how easy this is. All right. It gives all caps, so I hate that. Let's get rid of that. All right. So now, for pulse, the mean is 74, and the standard deviation is 12.5. Find the probability of pulse rate falling between 70 and 90. Okay, let me get rid of this thing here. All right, so I'm going to go into my draw mode. And I know that my mean is equal to 74. Well, let me write. It's not that easy to do this. 74. Wow, I don't want red. Okay. And my standard deviation is equal to 12.5. All right, now let's make the graph. Okay. Here's our z-axis. Here's our x-axis. So I made them local. So my z values I'll put on top, my x value is below. So right here, I know is 0. That's the mean. And down below would be 74. Now we want to know falling between 70, which would be right here, and 90 over here. So let's make a partition and shade the area that we want. Ooh, this is fun. Okay, so we're trying to find that area. So we need to convert our x scores into z scores. So we'll use the formula that z is equal to x minus the mean divided by the standard deviation. So our first z-score for 70 would be 70 minus 74 over 12.5. Now I will go to Desmos. Let's see. So I'll just do 70 minus 74 divided by 12.5. And we see that's negative 0.32. So my z-score is negative 0.32 up here. So negative 0.32. Beautiful. Now, how about for 90? What's my z-score going to be? Back to Desmos. And I'll do 90 minus 74 divided by the standard deviation, 12.5. And I get 1.28. So I go up here and I 1.28. All right, so now I'm going to go to negative 0.32 on my z table. The negative 0.32 is 0.3745. That means this area right here is 0.3745. And now if I do 1.28 on my chart, I get 0.8997. So that means this whole area is 0.8997. So the shaded area is going to be 0.8997 minus the 0.3745. So 0.8997 minus 0.3745 will equal to, look, I don't even have to regroup. Oh yeah, I hate regrouping. So the area of that shaded region is going to be 52.52%. What does that mean? It means that the likelihood of a pulse falling between 70 and 90, which we see is pretty high, is 52.52%. All right, so if you could do these problems that I've recorded and done in the slideshow, you'll be able to do your homework just fine. Hit me up if you're having some difficulty, but definitely watch this video over and over again, and you should be just dandy. Okay, everybody, thanks for listening. Let me stop my share. Turn on my video. Well, there I am, in case you forgot what I looked like. All right, thank you all, and have a great day.